In this lecture, I'm going to be talking about another approach for contrastive networks, which is called contrastive prototype sampling. And we are doing the task of relation extraction, but this time we are talking about temporal approach for relation extraction. So this is an example of temporal relation extraction. Temporal relation extraction aims to infer the temporal order of either two events in the document. Because of the nature of events in real life, there exist severe imbalanced temporal relation classes in the temporal relation extraction task. Even though various methods have been proposed to improve the overall performance, these methods' accuracy on small temporal classes is limited. One of the most severe issues in temporal relation extraction is the imbalanced data problem. Due to this, most temporal relation extraction models cannot perform well on small sample size classes. Intuitively, if we explicitly train a model to attend to the similarity distance between each sample and cluster similar samples together instead of modeling them independently like conventional classification models, the model could distinguish the small class samples from large classes based on the similarity measurement and clusters. Therefore, we propose to design a contrastive prototypical network to alleviate this problem. We present a contrastive prototypical learning framework to address this problem, which explicitly models the spatial similarity between instances in the embedding space so that instances from small classes can be distinguished from the large classes. To make it compatible with current temporal relation extraction settings, we propose a novel sampling memory queue-based methods so that the framework can be applied to a limited batch size scenario. And we further design a context encoding layer that incorporates both contextualized information and linguistic features such as tense information and dependency. This is the temporal relation distribution on just 4 popular datasets. From top to bottom, you see that from left to right, there are matrix, time bank dense, and different datasets. So this is the architecture. But first we do encoding. Everything goes to the encoding layer, and then the output goes to relation memory queue, which then we can pop up. But it also goes to this prototypical module because we have 2 modules. The contrastive module, which contrasts different pairs, and the prototypical module, which is like the previous lecture, which was some center points of the cluster. And so we have sample with Rayleigh distribution, and we sample uniform distribution for the contrastive. Then we augment, we add these losses together, and so the encoder layer is just using, we first use just a pre-trained language model such as BERT to encode and obtain contextualized embeddings for each token. And then we select 2 event triggers, E1, E sub 1 and C sub 2, and corresponding extractor embeddings. To further capture the temporal information between 2 events, we take into account 2 linguistic features, namely tense and part of speech tag. And so this is the architecture of encoding layer, that here we have linguistic features ready to be used together with the pre-trained language model, that BERT that I was talking about. And then we concatenate them so it produces a good representation. Then we introduce a relational graph convolutional network, stands for GCN, which incorporates information from multi-relational and multi-hop neighbors. And the representation of node I in its hidden layer is this. And there's the prototypical module. For each temporal relation, we first obtain a vector representation of input document with event triggers, where J is the J sample in the relation. Then for each temporal relation, we separate all the sample representations into two categories, the supporting set and the query set. We first get the centroid embeddings for each relation by averaging the embeddings in the support set. Then we use each representation, the query set, to calculate the Euclidean distance between each C and H. And we then we then calculate this prototypical loss. And R here is just the set of all temporal relation. The general idea of this loss is to push the samples that belong to one temporal relation closer to the centroid embedding of that relation. And for in-batch learning, during the training, we noticed that if we reduce the batch size, then not enough samples from small relation classes can be used to perform prototypical learning. Therefore, to apply the aforementioned approaches in the training inspired by the replay method in the incremental learning, we propose to use a memory queue to keep track of the support set in the prototypical learning. And then we maintain a fixed size queue for temporal relation for the prototypical module, and M is the size of the queue. Then we select N samples from the queue following this Rayleigh distribution. And Z here is the index of elements in the queue, and sigma here is the scale parameter, and we set it to just 0.5. The Rayleigh distribution used has a property that allows us more likely to sample representations that are closer to the current batch so that they are from the same document. This is the contrastive module, and we first sample K for T times from K sub J for temporal relation J, and then we have a set of different centroid embeddings for temporal relation by averaging each K. And we treat these centroid embeddings as positive pairs. And of course, these are negative pairs. And in the contrastive module, we care more about the difference between each temporal relation centroid embedding instead of in-batch difference. The representation should be from diverse documents. Therefore, the sampling process for K follows this uniform distribution. And finally, we compute this contrastive loss for temporal relation class J, and by just adopting info and CE loss, which I've explained it in a different lecture. So it is used to push the elements of the positive pairs closer to each other, while pushing elements in the negative pairs farther from each other. As its prototypical and contrastive modules demonstrate more on the small relation classes, we also include the conventional cross-entropy loss to evaluate relation classification so that the training is balanced. That is, during the training, we use the following laws to update the model, these lambdas are just hyperparameters. And during testing at the inference, we use the whole training set to obtain the centroid embeddings for each temporal relation class. This is the comparison, but this is the visualized clustering comparison between using the proposed method or not. And this denotes that the proposed method is enabled. And you see the performance with measures. Always we use precision recall F1 score for both micro and macro, because micro is more conservative, but macro could be more realistic.